Alright, hey guys, welcome back. Second set of notes for Chapter 15, Acids and Bases. Today we're going to leave the friendly territory of strong acids, where everything's logical and numbers are easy, and we're going to talk about weak acids. Weak acids are weak electrolytes. You'll recall from Gen Chem that electrolytes are substances that can conduct a current in solution, generally in water. And so here we have hydrofluoric acid. That's actually a weak acid plus water gives us the hydronium acid and the fluoride ion. Here you see two arrows because this is actually a reversible reaction. With strong acids we can just have a forward reaction. But with weak acids it's actually existing in an equilibrium where our bases are becoming an acid again. Here we have nitric acid, and it's the same thing there, and HSO4 is the same idea, it's a weak acid. Water is also a weak acid. So strong bases are strong electrolytes. So here's sodium hydroxide, it's a strong base, it's going to pretty much give up all hydroxide ions, and so we do a single arrow as opposed to that reversible arrow. Potassium hydroxide, same thing, in water, gives up potassium and hydroxide ions. So we do a single arrow, and here barium hydroxide. It is important to note when you have two here, it's actually going to give up both of those hydroxide ions. So that's something by now, if you've done those acid-base calculations from the first section of the chapter, you'll have realized that because we had to double their molarities. So if we go to weak bases, they're weak electrolytes. Again, here we have fluoride as the weak base, kind of accepting that hydrogen, and it's sort of a weak base. So we have the reversible arrows of the equation we had just earlier. So we're just taking the equations we used earlier for weak acids, and we're actually flipping them around to show weak bases. And then conjugate acid-base pair is something we've talked a little bit in class. The conjugate base of a strong acid has really no measurable strength, because of course if it were to accept the hydrogen as the conjugate base, it would go back to being a strong acid. And a strong acid is defined by its ability to release that hydrogen. So it really wouldn't be very strong as a base. Hydronium is the strongest acid that can exist in aqueous solution. It really wants to get rid of that extra hydrogen to become the very stable water molecule. And the hydroxide is the strongest base that can exist in aqueous solutions. It really wants to gain that extra hydrogen to become a very stable water. So here's a look at some conjugate acids, or rather some acids and conjugate bases. And here you can see as the strength of the acid increases, the base or conjugate base strength decreases. These arrows are going in opposite directions. So if we look at a strong acid, hydrochloric acid, at equilibrium we should expect equal hydrogen and chloride ions. If you look at a weak acid, a lot of that hydrofluoric acid is going to stay bound together as hydrofluoric acid, and it's pretty much just going to release a few hydrogen and fluorines. Not very many, it's going to stay as a lot of hydrogen fluoride. Whereas at equilibrium here, you can see there's no red column for hydrochloric acid. We're assuming that all that hydrochloric acid has pretty much been ionized, it's gone. So that's the idea there. So we can use this, we look at whether they're strong acids or weak acids, and we can perform these calculations. So we say, what's the pH of 2 times 10 to the negative third molar HNO3 solution? And we say, okay, well, nitric acid is a strong acid. It's 100% dissociated. And so then all we have to do is say our concentration of hydrogen ions is 2 times 10 to the negative third. pH is negative log of that. Done deal. They kind of draw it out as this long thing, which is fine. You can do that. Start and end. So we start with 0.002 molar. That's this here. We're going to end with 0 molar here. Or rather, we start 0, 0 here. We're doing like basically an ice initial change end. So we start with all acid and no base. We end with 0 because a strong acid completely dissociates. And we end with, from molar ratios, if we lose all of this 0.002, we'll gain this 0.002 here, and we'll gain this 0.002 here. You'll recall the ice charts we've been working on. And so, kind of like I said earlier, it's sort of a spoiler, but hopefully not. pH negative log of hydrogen, plug the value in there, 2.7. done deal. So barium hydroxide here, you could solve this with the equations that I kind of asked you to memorize. You could say this would be its concentration of hydroxides. It donates 2 per 1 molecule of barium hydroxide, so you could take that, multiply by 2, negative log of this gives you a POH, subtract that from 14, done deal. Or you could draw this out, which is fine. Barium hydroxide is a strong base, it's going to be 100% dissociated, and so you can write out its reaction. Barium hydroxide goes to barium into hydroxide ions. We start with the 1.8, and 0 of the ions, we end with a 0, and we gain 0.018 here because it's a 1 to 1 molar ratio, and because it's a 2 here, we multiply that by 2. That's what we gain there. And then we could say what our log of hydroxide ions here, and subtract that from 14, and you'd be set. So now let's get to the trickier one, weak acids and acid ionization constants. So here we have this very general formula, a hydrogen, because that's what acids must donate, plus A for just, acid. Any acid with a hydrogen in water makes hydronium, and the A- ion, which is just that whatever that acid is without the hydrogen. So we can kind of set this up in an equilibrium. AJ goes to hydrogen ions and acid ions and hydrogen ions go back to AJ. And we can set up an equilibrium constant for it. The equilibrium of this is the product concentrations divided by the reactant concentrations. It's probably just giving you a little bit of PTSD just seeing that after chapter 13 and 14. You're thinking, oh no, it's back. So Ka is something we call the acid ionization constant. Very similar to equilibrium. The higher the Ka, the stronger the acid. Make sense? Looking at this? The higher the Ka, the more product I have, the stronger my acid. The more ionized my acid is. Hopefully that's very, very straightforward. So here's a chart of some weak acids. Hydrofluoric acid, nitrous acid, all sorts of stuff. This is in your book, 15.3. You might want to dog-ear that page. You're going to use it a lot in the next section. It gives you its conjugate bases, which is fine, I guess, but those are pretty simple. Right now we want to worry mostly about the Ka. That's going to be very, very valuable for you in this next section. You're going to be very familiar with this. So now let's look at how we could do one of these. They give you the concentration of a weak acid, 0.5 molar of hydrofluoric acid. They want the pH. If this was a strong acid, take negative log of 0.5 and you're done. But it's not. It's a weak acid. So we're going to be a little trickier. We set up an equilibrium because it's weak. Hydrofluoric goes to hydrogen and fluorine. Fluorine and hydrogen go back to hydrofluoric. And we say our Ka is equal to our products over our reactants. And from the text, we find 7.1 times 10 to the negative 4. We go back to that chart and we find that value. So now we do the fun part. Ice, it's back. Initial change equilibrium. Oh no. All right. So initial will be easy, right? 0.5 here, 0, 0 for the ion. So that's not a problem. Now comes the tricky part because we don't really know exactly how much we're losing here. So we're going to have to say minus x, and since it's a 1-to-1 ratio, plus x plus x. And then we set up our equilibrium, which is 0.5 minus x, x, and x. So if you didn't get it last chapter, you'll have another opportunity to get it this chapter. So we set up our Ka with an x squared and a 0.5 minus x, which is just our products right here over our reactants right here, and we set it equal to k, which we got from the text. And now we solve for x using, again, the quadratic equation. So, oh boy, here we go. Our Ka in this example is going to be much, much, much less than 1. And so here they're going to cheat just a little. They say, okay, since our Ka is so teeny tiny baby small, then we can say that the x that we're changing from that is going to be teeny tiny baby small. So can we just basically say it's so close to 0 we can't include it in our calculations and just call it 0.5 minus x is pretty much closely to 0.5 and go with it? And that's what they do. We'll talk about when you can do that and when you won't want to do that. So we say Ka is about equal to x squared over 0.5, and they get the 7.1 times 10 to the minus 4, Then they solve using the, don't use the quadratic necessarily now, of course, multiply both sides by 0.5, square root of both sides, and it's a done deal. If you weren't sure, just use the quadratic. It's going to take you an extra couple minutes, but so what? You're going to know you're right, If you want to learn how to do the approximation, do the approximation. Either way, it'll be fine. So they find the x as 0.019 molar. Now our goal here is to get to pH. And to get to pH, we have to find hydrogen ions. Now we found x is 0.019. That's what we're losing, is 0.019. That's what we're gaining, is 0.019. So we just found the hydrogen ion concentration. It's 0.019. Negative log of that, and we're a done deal. So, negative log of hydrogen, 1.72. It's rather low pH, so we better make sure we're at an acid. Hydrofluoric's an acid. Kind of makes conceptual sense, and that's a done deal. So, when can we use this approximation, this weird little cheat thing where they just said, let's just get rid of x and call it good enough at 0.5? The answer is if your Ka is very, very small, much, much smaller than 1, which for weak acids it can be. And x has to be less than 5% of the value from which it's subtracted, which basically means we don't want to give ourselves too much error, assuming that this x isn't important enough to include. So in the last problem we had that it was 0.019, and our initial was 0.5 in the problem given to us. And so we take that and we find that it's about 3.8%. And so we can go ahead and say, we can drop the x. Less than 5%, you can make the approximation. And so here's the problem they gave us last time. Now, if they gave us this, pH of 0.05, we do the Ka as x squared over 0.05, we solve for it, and it's 0.006. We take 0.006 over 0.05, and we do that, and we find it's 12%. You can't use the approximation if it's above 5%. So that's how you find your approximations and whether or not you want to use those. If there's any doubt, do your quadratic. You know you have it right. Not a big deal. So you got to solve for x. You either use the quadratic equation or successive approximations, which is taking that x out. So how do we solve it? Number one, identify major species that it can affect the pH. Ideally, there's only one, and then it's going to be pretty easy to work with. In most cases, you can ignore water. It's, very, very small pH change from water. Ignore the hydroxide ions because it's determined by hydrogen ions. Use ice, again, to express equilibrium concentrations in terms of x. Write the Ka. Solve for x by the approximation method, or solve for x exactly. Either way, it's going to get you very close to the same answer. Calculate the concentrations of all the species, or the pH, whatever they're asking you to calculate. And so here we can see one where they don't actually give us the identity of the acid, and that's fine, because we can still write out that general equation. So what's the pH of 0.122 molar monoprotic acid if its Ka is 5.7 times 10 to the negative 4? So we can write out an equation. General formula for an acid, Ha, goes to hydrogen ions and acid, make it an equilibrium constant. Monoprotic acid, there's your initial, 0, 0. There's our constant. We're going to solve it exactly the same way. So ice, our initial is 0.122, 0 and 0. Ha is going to be a minus x, hydrogen's a plus x, acid's a plus x. Our equilibrium, we do 0.122 minus x, plus x plus x. You set your K equal to the x squared over 0.122 minus x. You find that your K is much smaller than 1, so you can use the approximation method if you'd like. You can use a quadratic if you like. Doesn't matter, you're going to get the right answer. K is x squared over 0.122. And so you solve for your x, you get about 7 times 10 to the negative 5th is x squared, so you take the square root of both sides, you get an x equal to 0.083. That'd be your hydrogen ion concentration, because it's just equal to x. Negative log of that gives you pH. Done deal. So here they did, to find out if the approximation was valid or not, they solved for x and then divided it by 0.122, which was our initial concentration. And they found that it's 6.8. So they actually probably shouldn't use that approximation. They need to go ahead and step back to here and use the entire quadratic. So more than 5%, it's not okay to do that. So they stepped back and did the quadratic to solve it and get it correct. So here they're taking their problem back to that second step and setting it all equal to 0. Excuse me. Solving it with the quadratic, which we're familiar with at this point. And they find that their two concentrations can be a 0.08 or a negative 0.08. They get rid of the negative because you can't have a negative concentration of hydrogens. And then they sub it back into this to find their hydrogen ions. Negative log of those. You're at a pH at 2. You're talking about an acid. That's reasonably logical. And you can move on. So I'll just be honest with you. I default to the quadratic because by the time I take the time to calculate x and find out if it's 5%, I probably could have done the quadratic and just been done with the problem. So I just do the quadratic right away. The more I do it, the quicker I get at it, and I know I'm getting it right. So I know the whole AP test is a timed thing, but that's kind of where I'm defaulting to at this point. So we can use these problems to find what's called a percent ionization. This is pretty logical, actually. Percent ionization, an acid ionizes when it breaks apart into charged ions. And so it's the ionized acid concentration at equilibrium divided by the initial concentration of the acid multiplied by 100%. So here's how you can do this. For a monoprotic acid, it is H plus how much acid we've given up, how much hydrogen we've given up, divided by what our concentration was of the acid to start with, multiplied by 100%. So pretty logical stuff, What's our percent ionization? Well, it's how much hydrogen we've given up over your total, just like calculating a grade or anything else. And so here you see a strong acid, is going to ionize pretty much 100% all the time. For a weak acid, as we increase that concentration, we actually change our percent ionization. It really drops pretty fast. Less and less ionization, the less concentrated your acid is, which sort of makes sense. Alrighty, so weak bases and base ionization constants is where we will end. That's a new section of the book, so we'll do a separate lecture on that. So thank you.